All right, welcome everybody. I hope it's not too distorted, you can see everything. Great. So let's start with lecture 9 in our series on game AI. Last time we did something interesting, and so therefore we shall recap that. And then, once we're done with that, we'll address a new topic, namely the topic of path planning. In order to understand how we can approach the problem of path planning, we again first have to look into lots of basic concepts from the area of graph theory, and then it is time to study two of the most famous algorithms of all computer science, namely the Dijkstra's algorithm and an improvement on it called the A-star algorithm. Maybe you have seen these two algorithms before, I don't know. Typically they are being taught in many computer science curricula, so maybe you have seen that, so let's hope that there will be something new for you anyway. And once we are done with that, we of course summarize what we have learned today. So, what did we do last time, and actually the last couple of times we met? We studied the problem of problem solving, in particular using the idea of tree searches. And one of the ideas we had to consider so-called uniform tree searches, where we consider state space. That could, for instance, be states during a game of tic-tac-toe or chess or whatever, and every state in such a turn-based two-player game has a couple of successor states, and these successor states too have successor states, so there is the notion of a state space. But we also already saw that problems such as finding a route to travel from point A to point B on some map could also be thought of as a problem of, could be formalized as a state space where different locations on that map would form the states, and transitions from one location to the other would sort of define the structure of the state space. Right? And whenever we are dealing with problems that we can, in a sense, reduce to a state space representation, we saw that we can use tree search algorithms in order to solve problems that have to do with these kind of structures. And the classical tree search algorithms we studied so far were the idea of depth-first search. You see the example of where we expanding a state and not. That leads us to a state N1, which we then have expanded to a state N5, which led to a state N13, 14, and 15. No solution was found in that particular sub-branch of the tree that is being developed by expanding states. So we had to backtrack, go back to node or state N1. From there we expanded a state N6, and that apparently was the solution in this example. Right? So you see every node in this tree that is being uncovered in this example corresponds to a state, and the search for a goal state is basically a tree walk procedure. There is some way we walk down a tree, and that tree, as it so happens, is being built while we are trying to solve the problem. Again, in all the examples I'm showing you, we actually see the whole tree, but in practice, of course, that tree is not given, but comes into being while expanding states. And this expansion procedure actually creates a tree structure. Now, these depth-first searches are very mechanical, because basically in this approach to tree search, we always expand a node in the fringe, which is the set of nodes we want to or have to expand further. In depth-first search, we always expand the deepest node in the current fringe. If there are several on the same level, we have to pick one of them up. It's basically we expand nodes that are residing on a deeper level of the tree first. That is of terrible runtime complexity, basically O of b to the m, where b again is the branching factor of the tree, that is the average, say, average number of possible successors of every state, and m is the deepest level, it's the counter of the deepest level. We saw that we can prove on simple depth-first searches by introducing ideas such as alpha-beta pruning, where the complexity would go down to a factor, to a behavior of O of B raised to the C times M, and that C is a constant less or equal than 1. So that may not help in practice, but typically it does. So in the worst case, this C would actually be 1, then we don't gain anything. Usually it is less than 1 and we are happy. We also studied the notion of breadth-first searches. You see an example on the right-hand side. There, instead of expanding the deepest fringe node, we basically expand the shallowest fringe node. This leads to a level-wise exploration of the state space. And again, I'm using these terms, search tree and state space, I'm using them interchangeably because they are in a sense the same thing. Of course, like in reality, they are not exactly the same thing, but there is a one-to-one relationship. Yeah, and we also looked into the idea of depth-restricted searches. I have shaded it a bit because it is not quite as mechanical as the other 3 approaches here, so it's not as uninformed as these 3 approaches to tree search, and we will look into that more closely in a couple of minutes. And then also recall that I already pointed out that it might not necessarily be a good idea to select nodes or states for further expansion and thus exploration in a purely mechanical way. We could, for instance, just select them randomly. Right? That is, we could try to come up with ideas as to how to realize probabilistic searches. This is the basically other main branch in this area, instead of expanding nodes purely mechanically just based on the structure of the state space, we could try again to do that in a more informed manner by using evaluation functions or heuristics, which we may use to rank the nodes in the current fringe or with respect to their merit for further expansion. Right? So that would lead to the idea of best first search. We will come back to that. Last time we spent a whole lecture on the idea of Monte Carlo methods, in particular, of course, in the context of tree searches. And there is this idea of Monte Carlo tree search, and that is one of these probabilistic approaches. And the major benefit of this approach to tree search is that it is of a fixed number of iterations, or it requires a fixed number of iterations to expand the search tree. It does not really depend on the branching factor anymore. In the end it does, but not really explicitly. We saw that each of these iterations that are carried out in the Monte Carlo tree search algorithm consists of 2 phases. The first phase, let's call it the bandit phase, after what we have discussed last time when we looked into the multi-armed bandit problem. In the bandit phase, what Monte Carlo tree search does is the following. We start our exploration of the state space, that is our expansion of the search tree, typically at the beginning with the root node. And then we check if that node we start our current iteration with has been fully expanded or not. If it has been fully expanded, that is to say it is not a fringe node anymore, and therefore it has all its possible successor states are already available in our search tree. So then we have to pick, or what this algorithm does is it picks a successor state according to some probabilistic measures or information. They are ranked. There's some expectations as to how auspicious one of these, all of these successor states of the current node are. And we then descend to one of these successors. And with this successor, we call this algorithm recursively. If this successor has been fully expanded, the same thing happens. And this phase, or this regime of the Monte Carlo tree search, is recursively iterated until we hit a fringe node. So in this bandit phase, we typically start with the root and then proceed down the levels of the tree that, or the nodes of the tree that have been uncovered or explored already, until we hit a fringe node, this one in this example. So in this example, Monte Carlo tree search in this iteration started with the root node, then went down to N2, from there to N6, and then hit N16, which is a fringe node. And in this situation, the second phase or regime takes over. Now from N6, which is a node that has not been fully expanded yet, we randomly generate a successor state. Something that could happen after we have reached the state represented by node N16. And that leads to a new node or a new state. We shouldn't call them nodes because the states that are being explored in this second regime are not actually added to the search tree. It leads to a new state, which we again expand randomly, and we continue with these expansions, these purely random expansions, until we hit a state that corresponds to a terminal state, say, of the game we are dealing with. If it is a terminal state, we can compute the utility of that state for the player who is about to move. Once we have this utility, we can then pass it back up the tree, and we will register this newly found utility value with all the nodes in the current search tree, that is with all the nodes that have been expanded already, that are part of the search tree already. And if this two-step algorithm is repeated a lot of times, then we will detect and uncover more and more states within the state space we're dealing with. And the search tree will grow, because once we hit a fringe node, we expand it and add that newly expanded node to the search tree, and from there we walk until we hit a terminal state. So this tree will grow iteratively in a fixed numbers of iteration, and in each iteration we will eventually reach a terminal state or a leaf node of a search tree which is not fully uncovered yet. There we find some utility values which will be passed back up, so we create a statistics as to the usefulness or utility of certain branches in this tree, and after a large number of iterations, the top level nodes of this tree will have numbers assigned to them that somehow are representative of the value of the corresponding branch. And once we are done with the fixed numbers of iterations, as the player who has to move, we move to that state with the best payoff. This is Monte Carlo tree search. It is of the order O of m, like the complexity of design, because basically in every iteration we have to perform this two tree walk and random walk procedures until we eventually hit a terminal state, which is to say until we sort of arrive at the leaf level of this tree. If the deepest leaves reside on level m, then it's O of m. But we have to do that a lot of times, in particular if there are many possible successors for every state. In order to get reliable statistics, this has to be repeated a lot of times. And still, it is of a complexity that is less than these uninformed search algorithms we've seen so far. You have a question?
Yes. In the case we have already, like in the first case, after on the fringe node 16,
yeah,
we already expanded left part. So if we run the second time, our on the second iteration, if we appear to be on the fringe node 16 still,
yeah.
What is the, like? Will it somehow exclude the path it already?
Yeah. If you hit a fringe node that has not fully been expanded yet, you typically generate a successor state you have not considered so far.
Ah, okay.
So, and this is to grow the tree. So in every iteration there will be one node added to the tree. So say in the next, say this is iteration t, and in iteration t plus 1, we again reach this fringe node, then it would expand this node, which as it so happens is a leaf node, but that node would then be added to the tree. There is no random walk because that newly expanded node is already a leaf node.
Yeah.
But, yeah.
So on the second step is not fully, again, randomly, it is also a semi-random step.
The selection of the nodes to expand?
Yes.
Yeah, yeah. This is more random than the question of how to choose a branch where to descend, but it's not as totally random as the random walk phase. But the question, like, once we reach a node like that the second time, what successor to expand is also a random choice. Not quite so.
Second
Yeah.
question, just to make sure I've got the idea. So we repeat these iterations until we converge, right? So
no, you cannot. I mean, you can, but that will probably take infinitely many iterations.
By convergence, I mean, like, if, like, after 1,000 iterations, for example, our, like, algorithm still chooses the second node and then 6th node and then 16th node, then we
yeah, but this is the exploitation dilemma we discussed last time. It can actually happen that for, you know, freakish reasons, a certain branch is of higher utility, and then it will be chosen more frequently. Right? Of course, if you have established after 100 iterations that, you know, this branch is of so much higher utility than the others, you can basically stop your search, right? Because then you have, in the situation you're in right now, found an auspicious successor state. So for instance, if after 1,000 searches you know that the last successor, the third one of the root node, definitely has a much higher utility than the other two, but then why continue your exploration? You now know after 1,000 random probes that obviously the third one is, in the situation you're in right now, the best one to go for. Right? If you were to do 1,000 iterations with a silly tree like this, you basically have min-max in the end. This converges to min-max if you run it like infinitely many times. And if the tree is really small, then you don't have to do 1,000 iterations.
So basically, our stopping, like, criteria is just only the number of iterations.
Yeah, and really, it of course very crucially depends on the branching factor. So this is crazy because the runtime effort of this algorithm does not, but the quality does. Say if every of these nodes would have 100 successors. So a humongous tree, right? Because the root node would have 100 successors, every successor would have 100 successors. You have to probe a state space like this, you know, a lot of times in order to finally have a reliable statistics as to where to go. And therefore, again, the runtime complexity is basically just the question, okay, how often do we have to go down to the leaf level? It's this capital T in this but this capital T is extremely crucial. The number of iterations, this fixed number of iterations you carry out seriously depends on the problem at hand. If the problem is trivial, you know, I did it 25 times and it didn't improve anymore. Purely random choices. If that would have a large branching factor, yeah, then be prepared to do this like 1,000,000 times. No, seriously, I mean, at least, right? The node selection in this first phase, in the bandit phase, is probabilistic. And by that I mean, again, so we start, say, the next iteration of this algorithm at the root node of the tree. We have to decide for a branch to further explore. And that does not happen purely at random, but there are sort of weights, right? Prior probabilities, if you want, that would prime us for a certain branch to consider further. This is what I mean by probabilistic. There is statistical information we can use in order to decide which branch we should explore further. In this second phase, in this random walk phase, once we have hit the fringe and from there, you know, play the game until we hit the terminal state, this is purely random. There is no prior information. Basically, in this phase of the algorithm, you just generate successor states that comply with the rules of the game, of course, but you do not have any preference for any successor state. You just do this until the game terminates, you evaluate the state, you pass that information back up the tree. And in this sense, well, the approach does, of course, require functions that mimic the game mechanics, because you have to create successor states, and therefore you need to know about the game rules. But the evaluation of game states does not require any additional information or human ingenuity about the nature of the game. The evaluation is basically really done based on these statistics you gather from passing back up utility values from the leaf level of the tree. This is very attractive. This is very attractive because, as we saw in chess, there are these more than 8,000 features where somebody must have thought of it is probably a good idea to consider this feature to evaluate a chess state, and then we should probably also look into this feature. Why stop at 8,000? Why not 1,000,000? And who is to come up with all these million features? Of course, we can try to create algorithms that automatically learn what kind of features are interesting to consider. That, you know, can be done, but it may take a very long time. Here, the benefit is we do not have to worry about features. This will come up with a weighted tree, if you wish, without having to compute features. It just computes utilities in terminal states and passes them back up and creates average or expectations or minima or maximum, whatever. So this is a very auspicious technique, and as we discussed last time, a rather recent technique. So there is still a lot of ongoing research in this area, and I will therefore leave it at that. It is good for you to have seen this idea, because I know some of you actually wanted to work in the gaming industry. Now you know what you can tell them during your job interviews. It is good to have seen this, but we will keep it at that, because from this point onwards it's like lots of nasty technical details. So, and therefore we will now return to classical tree search algorithms, because so far we have explored uninformed searches, and of course the idea of informed searches is nothing new. It's a very venerable idea as well, and that is again to say that our criterion for expanding states of the state space we want to explore is not purely mechanical, such as deepest node in the fringe, shallowest node in the fringe, but actually is informed by a certain heuristic. And we will look into that in particular by means of the example of path planning. And if you remember from lecture 7, I once had to go to Bremen in order to give a lecture on game AI, and thus was faced with the problem of having to plan a trip from Bonn to Bremen, and I was sort of considering doing that trip by train. So there was a state space which basically corresponds to a part of the railroad network of Deutsche Bahn, northwestern Germany. There are lots of sort of hubs in the railroad network. The question was like, from Bonn to which hub do I have to travel next, and from there where do I have to travel next, and so on and so forth, until I would eventually reach Bremen. This is a path planning problem. The interesting thing about this planning problem is not necessarily just a shortest distance problem, but probably also a resource minimization problem. So distance should be short, and the amount of money I would have to pay should not be too high as well. So there are two criteria, and therefore we have to come up with a plan as to how to get from Bonn to Bremen. That does not take too much time. It's a short trip, and also does not cost too much money. And we'll look into how that can be done right now. However, our focus will be more on like geometric distances rather than on economic considerations such as I don't want to spend too much money on this. Let's keep it simple. So, and also in lecture 7, we already formalized the notion of a well-defined problem. So basically, we can agree that this problem of path planning is a graph search problem. We have to search a path in a graph, and a graph is something we can imagine as a discrete state space. So we are dealing with a graph search problem, and in order for it to be solvable, it should be well defined. We looked into the notion of a well-defined problem, saw that it is composed of 4 ingredients, where the first one is that there has to be an initial state or initial node. Again, I'm using these things interchangeably. An initial state from where we start our search, and there also should be a goal state or possibly a couple of goal states. That is a state we want to actually reach. In order to do that, we have to have the notion of a successor function, and we can think of this successor function actually as a representation of actions that are available to us. So to be more specific, say if I am in the city of Bonn, there are lots of actions available to me. For instance, I could travel to the city of Aachen, or I could travel to the city of Cologne. These are 2 actions available to me when I am in state Bonn, and the successor function would model that. Right? Typically, the successor function does not model the actual action, but rather its outcome, namely the successor state. And in that sense, 2 possible successors of the state Bonn would be Aachen or Cologne. If we have this successor function, we of course can use that to expand the state we're in. That will help us to, sort of have an idea as to what possible states can be reached from where we are right now. And we have to evaluate these possible states, these alternatives. We have to have a goal test function that would decide if one of the successors we are probably considering right now is actually the state we want to reach, or one of the states we want to reach. And we have to have a path cost function, because in this example I'm showing you here, say we want to travel from the vertex labeled 0 to the vertex labeled 10. There are many possibilities for how to do that. Right? We could go from 0 to 2 to 5 to 10, that looks very good. But we could also go from 0 to 1 to 3 to 7 to 1 to 4 to 8 to 10. Both would be paths that lead us from node vertex 0 to vertex 10. One of them might be preferable, probably the shorter one. We have to have a way of deciding which of a set of possible paths we can find is the one we should go for. And for that, we need this cost function, which assigns numeric values to paths we uncover throughout our search. And yeah, we can think of these paths as a sequence of states. Obviously, like in our state space, in this example, a path would just be a sequence of vertices which are related through moves. So a path is a sequence of vertices where between any 2 subsequent vertices there is an edge. And a solution has to be a path that starts in the initial state and ends in the or one of the goal states. This is a solution. What does that have to do with computer games? After all, this is a lecture on game AI. I know that you are playing real-time strategy games. Mm-hmm. So where is path planning of importance in computer games?
For example, in Skyrim, you can have a friend. Right?
Yeah, yeah.
So, and if you are jumping from the mountain,
yeah,
it doesn't follow you. So it is Rater choosing roads to follow you.
Yeah,
so
very nice. Yeah,
the optimal.
Yeah.
So
So he's pointing out that in games like Skyrim, you can be accompanied by non-player characters. So you are controlling an avatar character in these games, and maybe you have a friend who is always following you and joining you in battles and whatever. And sometimes you, as the human player, may do stupid things, such as jumping down a mountain or whatever. These are things the non-player characters typically don't do. And once you have jumped down a mountain and from there traveled somewhere else, eventually your friend will join you again. And in order for the game to be realistic, that may take some time, because the friend will have to take a route throughout the game world. Of course, for that purpose, the non-player character has to actually find a route from the mountain he didn't jump off from, or she, but say to the next village, whatever. Yeah, that's true. This is indeed where these things come into importance. But of course, like for instance, very important in these real-time strategy games where you're controlling teams of whatever units, and you say, okay, this unit now has to do something here, and then for the game to be realistic, the unit of little agents has to find a path through the game world to reach the destination where you want them to do some work. And so actually a lot of research on path planning in games focuses on real-time strategy games. But consider this dungeon here. What we see is a map, so a very simple two-dimensional game world. There is this is a part of a map, a room, say, with 1, 2, 3, 4 entries or exits. And let's assume that you have a non-player character that, for whatever reason, has to travel from this source location to the green target location. And this is a game map. We saw that we can model the geography of northwestern Germany in like a very abstract manner using this graph of railroad hubs. So why not modeling the geography of this dungeon, say, in terms of a graph? I'm using a grid graph here. It's a graph of regular spaced nodes. This is a graph like these gray dots and the black edges define a graph. There are walls which sort of disrupt the regular nature of this grid. The problem we are facing as game programmers is to come up with an algorithm that would allow an agent entering this dungeon at this point to find its way to that point. Right? And the solution could look like this. Right. This is indeed the shortest path from this point to that point, if we are using one of the algorithms we will look into later on. We can already see that shortest path is not necessarily the most convincing path. So probably a human player would more go like this, so more rounded paths, or not these right angle paths. But given the representation of this dungeon in terms of this regular graph, this is what a graph search algorithm would come up with. But as we can sort of beautify these paths. Here what I did is I computed a potential field. We will talk about that next time. And sort of created another shortest path where it's not just distances between nodes, but also values of these potential fields. Anyway, path planning is crucial in computer game AI, and let's study how to approach it. But first, we have to familiarize ourselves with many concepts from graph theory, because I will use this terminology. And so in order for you to be able to follow me, we have to familiarize ourselves. Let's start. We already talked about graphs, and we said that a graph G is a tuple consisting of two sets. One is called V for vertices, the other is called E for edges. So the set of vertices is basically a discrete set of something, and very abstractly we just call them vertices. and I will call them V1 up to Vn. There is an example. V1 would actually be vertex 0, and Vn would be vertex 10. So there we have 11 vertices. Here you can see them. This is the vertex set in this example. The edges are a relation among vertices, so that is a subset of the Cartesian product of V by itself. For instance, one edge is an edge from vertex 0 to 1, and this is the tuple of 0 and 1. Another is the edge from 0 to 2 is the tuple of 0 and 2. So there you have it. This is a graph. Nothing special about this. We have talked about this. Sometimes you also find the elements of V called nodes, and I might do that. I may call them vertices or nodes. I really don't care. It's the same thing. And also the elements of E, you will find them to be called edges, arcs, or links. And depending on my mood, I'll use any of these terms. They are the same. Just for the sake of completeness, a multigraph is a graph where we have vertices or nodes, but there might be several edges between any two vertices. So this is a multigraph. A labeled graph is a four-tuple. I'll use the Greek letter gamma in today's lecture just to make sure that there is a difference between a graph and a labeled graph. I will drop that distinction later. But a labeled graph is a four-tuple, again consisting of vertices and edges. That in addition to a conventional graph, we have two further components. I'll call the one LV and the other LE, and these are functions that map, the LV function maps from the set of vertices to a set of labels, capital LV, and LE maps from the set of edges to LE, edge labels. And, you know, to make a long story short, look at this example. Here, what I have done is created, a function that maps vertices to labels and edges to labels. In particular, I have chosen the vertex labels to be two-dimensional vectors. Right? So every vertex in this example now carries a vector. This is the label of the vertex. The thing inside this circle is the name of the vertex, and the sort of subscript is its label. And this is just a two-dimensional location. This is a two-dimensional surface. We can position these vertices, and then why not, use their locations as their labels. And I've also labeled the edges. I don't know if you can read it, but for instance, the edge between 6 and 7 is labeled 0.4, and that so happens to be the distance between the two vertex labels of 6 and 7. Right? So we have a location attached to vertex 6, a location attached to vertex 7. We can compute the Euclidean distance. This is a real number. We use this real number as the edge label. There you have it. This is a labeled graph. The important thing is we have two more components which are functions, which take the vertices as their domain, map it to something, and the other function takes the edges as the domain and maps that to something. A directed graph, again already talked about, is a graph where each edge is an ordered pair. So in a directed graph, the order of the two elements of that tuple, the IVJ, does matter. So for instance, in this graph, we see that there is an edge tuple called 3, 6, because this edge points from 3 to 6. These are supposed to be arrowheads that indicate the direction of the edges. Order does matter in directed graphs. A graph is symmetric if it is a directed graph, where for every edge, the IVJ, there's also an edge, VJVI. If there was an edge pointing from 6 to 3, and for every other directed edge there would also be an edge pointing in the other direction, then that graph would be symmetric. Well, then we can define an undirected graph, because if we have two edges between any two nodes, we can basically define them to be equivalent. So if we say order does not matter, it's a symmetric graph, but order does not matter. These pairs here form an equivalence class. Well, then in that case we drop the arrowheads. We don't draw two edges, we just draw one, and we call it an undirected graph. A subgraph of a graph G is a graph G prime, which is again a tuple, this time consisting of V prime and E prime, where the V prime is a subset of V. So in a subgraph, the vertices of the subgraph of a graph G are a subset of the vertices of G, and so are the edges of the subgraph. The edges of the subgraph are a subset of the edges of the embedding graph. Here you can see an example. We have the graph we have been looking at for a couple of slides already, and I have emphasized a certain subgraph. Just there's no semantics attached to that subgraph. I just, emphasized a couple of edges and nodes and call that a subgraph of the graph. And it is. We already talked about a path where we need a formal notation for path. So we said a path is a sequence of k vertices. Let's specify the number of vertices in a path. Some vertex vi1, and then some vertex vi2, and then some vertices until eventually we end up at some vertex eik. So a path is a sequence of 1, 2, up to k vertices. Path of length k. And because it's really, messy to write these many arrows all the time, I am using the notation shown on the upper right. So a path of k vertices starting in some vertex vi1, ending in some vertex vik, is indicated by this arrow with the star on top of it. This is my way of writing down path of length k between some vertex and another vertex. And here is an example. This is a path from vertex v6 to vertex v9. A cycle in a path, a cycle in a graph is a path where the end, where the initial and the end vertex coincide. This is a cycle. Say we start in v2 and then have a path that ends in v2. I am emphasizing this because here's another cycle. We start in v2 and then go to v1 and then go like that. So this is a path, which is a cycle. If the initial vertex and the end vertex are the same. It does not have to look circular. Right? This is important. This is why I'm pointing that out. If you read cycle, you think of something circular, but in a graph that does not necessarily have to be circular. Right? The path we don't know. Just from looking at it, we could go like so, whatever. If it starts in v2 and ends in v2, it's a cycle. If there are lots of sort of explorations that sort of poke out of this circular structure, it could be a cycle. You never know. Yeah?
Just curious, by your notation, how you are going to emphasize that the first cycle is different from the second one?
Oh, this you cannot. You cannot. But yeah, well, okay, so I could, but probably also adding a subscript to the star indicating the number of steps. Right? Yeah. This notation is actually not. And also, like, you are
also going to end up with a problem. I mean,
yeah.
We are going to optimize the path, right?
Yep,
so, and in this notation, we are just saying from v6 and v9.
Yep.
And how we are going to say that.
No, but I'm glad about your question. So he asked, like, what happens if we cannot use this notation to distinguish this path from this path. I don't want to. I just need something to indicate path of more than one step. Okay. This is all I need, right? And yeah, if we would have to, we could probably use some subscript or superscript at the star, whatever. I don't really care. I just want to have something where I can write path instead of lengthy sequences of vertices and arrows and comprise that into just one vertex, two vertices and one arrow. A weighted graph, well, we are nearing the end now. A weighted graph is a labeled graph where the thing we are most interested in are the edge labels. And that is to say, a weighted graph. In a weighted graph, we don't necessarily need to have a function that assigns labels to vertices, but it has to have a function that assigns labels to edges. Right? If the edges carry weights which happen to be real numbers, then it is a weighted graph. And the path length, or path weight, or path cost in a weighted graph is just the sum of the weights of the edges traversed in a path. And the shortest path from Vi to Vj, some arbitrary vertices in the graph, is a path that starts in Vi and ends in Vj. This is all I need to indicate. I really don't care about the details of it. But it's a path from Vi to Vj of minimal cost. That's all I need to have. And yeah, there's another interesting notion, the notion of the graph diameter. If we were to know every shortest path in a graph, like so we look at every vertex as a potential start vertex and every vertex as a potential end vertex, then we can compute the shortest path from any vertex to any other vertex. And the longest such shortest path is called the diameter of the graph. Let's see, do I have a graph here? Yeah. What would be the diameter of this graph? Is 5, because from 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, there are two nodes that are 5 steps away from this node 6 here. Note that by calling the diameter 5, I implicitly assumed the edge weights to be 1. Do you see that? And so I was just summing the number of steps. And it turns out there are a couple of nodes that are 5 steps away from each other. So the diameter of this graph would be 5. Because that is the longest, shortest, but like the shortest path between any two vertices we find is 1. Sure, right there are path of length 2, 1, 2. There are a couple of paths of length 5. This is the diameter. A connected graph is a graph where there is a path from any vertex to any other vertex. This is a connected graph. This is an unconnected graph. We could say this is two graphs, but sometimes we call this just one graph. But note that there is no path from vertex 6 to vertex 2, say. We cannot reach vertex 2 from vertex 6, so that graph is unconnected. The important thing is the notion of the connected graph, because in a couple of minutes, this algorithm works for connected graphs. Now you know a connected graph is where you can reach any node from any other. And because it's so beautiful, and we'll need that later on, let's look into the notion of the degree of a vertex. This is denoted using d of Vi, where Vi is some vertex in the graph. It is the number of edges incident to vertex Vi. Here you see an example. There are two edges, well, either ending in vertex 0 or leaving vertex 0. We do not distinguish those. We say there are two edges incident to vertex 0. So the degree of vertex 0 is 2. Right? And by the same token, the degree of vertex 1 is 5, because there are 5 edges that either end or start in vertex 1. And you can take it from there. I said we do not distinguish edges, or the fact of try to distinguish whether an edge ends in vertex 0 or starts in vertex 0. However, if the graph was directed, then we can distinguish that, and we can specify this notion of the degree of a vertex to the in degree. That would be the number of edges pointing to a vertex, and the out degree would be the number of edges leaving that vertex. Yeah, sometimes the maximum degree is called capital delta of G and the minimum lowercase delta. We don't really need that right now. And then the adjacency matrix of a graph is something we have already talked about. If there is a graph consisting of vertices and edges, and we have n vertices, so the size of the set V, the number of elements in V is n, then the adjacency matrix is an n times n matrix, such that an entry aij is equal to 1 if there is an edge between vertex I and vertex j. If that is not the case, this entry would be 0. And here is an example. So, let's look at vertex 0, that is sort of the first row in this adjacency matrix. There is no edge from 0 to 0. In all the examples I'm presenting here, we exclude self-transitions. So there are no edges from a node to itself, and therefore the diagonal of this adjacency matrix is 0. There's only zeros along the diagonal. But there is an edge from node 0 to node 1, and this is indicated by this 1 here. Right, so row 0, column 1, there is 1 because there is an edge from 0 to 1. And the same goes for node 0 and node 2. Row 0, column 2, there's a 1 there. Right? No big deal. We could trace all the ones in this adjacency matrix. This is a representation of, I can already give it away, the topology of this graph. We'll come back to that next time. An interesting fact about adjacency matrices is if we choose them such that their entries are either 1 or 0, we can compute their powers. For instance, A squared, this is matrix A times matrix A. And then we find, for instance, that in a 0, 0 entry of A squared, there's a 2 now. And this 2 indicates the number of paths from vertex 0 to vertex 0 of length 2. Is that right? Are there 2 paths from vertex 0 to vertex 0?
0, 1, 1, 0.
Exactly, you say 0, 1, 1, 0. That's the first one. And the other? 0, 2, 2, 0. There are 2 paths of length 2 starting in 0 and ending in 0. Let's see, how many paths are there of length 2 starting in 0, ending in, so column 0, row 0, column 1. How many paths are there starting in 0, ending in 1 of length 2? There's 1 path because we can go from 0 to 2 and then to 1. So we have a path of length 2 from 0 to 1. And these facts are gathered in the square of the adjacency matrix. Right, so we can square the adjacency matrix to at least compute the number of paths between a start vertex and an end vertex of a certain length, 2 in our example. We cannot read those paths from the adjacency matrix, but we know there are so and so many of this and this length. Of course, this works for higher powers as well, so this would indicate the number of paths of length 4. So for instance, now there are supposedly 13 paths from 0 to 0 of length 4. Let's see, this is a path of length 4 from 0 to 0. This is a path of length 4 from 0 to 0. you see, I mean, there are many of them apparently, right? And the more, the higher powers we consider, then this quickly explodes. This quickly explodes, right? This is the curse of combinatorics, in a sense, right? Note the following. With respect to path lengths of 4, where again I'm just assuming, or let's say step counts of 4, because I am implicitly labeling all the edges with a 1, which is basically to say that a path in this simplified point of view is just the number of steps between 2 nodes. There are apparently no paths of length 4 between vertex 10 and which one is this? 10, 9, 8, and 6. So there is no path of length 4 between 10 and 6. And apparently there's also no path of length 4 between 9 and 6. this makes sense, right? Because we already established that the length of these hop counts, or the number of hop counts from 6 to 10 or 9 is 5. And therefore, indeed, in the fourth power of the adjacency matrix, this is still reflected. There is no path of length 4. If we compute the sixth power, we all of a sudden find that there are 14 and 10 paths of length 6. I did not show the fifth power of the adjacency matrix, but in the fifth power, these two zeros would have been replaced by, I don't know, like there's actually 2 paths here, or whatever, how many paths there are, but then there would have been entries different than 0. Now in the sixth power, like, what can we read from this matrix actually? Like that eventually we have, by taking consecutive products of the adjacency matrix with itself and then ending up with matrices that do not contain zeros anymore, can we read an important fact from that? Yeah, that is probably one way of determining the diameter, like because we know it has to be between 4 and 6. But we also know that the graph is connected, right? Because if it was not, there would still be zeros in here. And so just from, you know, computing powers of the adjacency matrix and eventually, say, finding an adjacent power of the adjacency matrix that does not contain zeros anymore, we know this is a connected graph. Okay, this is fun, and it indeed plays an important role in what is called the diffusion, like dynamic processes on graphs, like starting somewhere, ending somewhere. We can read a lot from these powers of adjacency matrices, but generally it is very expensive to compute them. Right? Matrix multiplication, so A times A is of the order of n cubed, right? And if that n is large, this is very expensive. And in particular, if we want to compute not just the product of A with itself, but computing this A times A times A times A times A times A hundreds of times, this will take a while, even on modern computers, if the graph is large. There are powerful algorithms for matrix multiplication, and beginning with the work of Strassen, I guess. It was pushed down from n to the third, and now we are at about n to the 2.3, which is much more efficient than n to the third, but still it is very expensive to compute powers a raised to the p if n and p are large. What can we do? We can use the spectral theorem. Make clever use of the spectral theorem. And I know for those of you who have been with me for a couple of semesters already, you might say, oh, not again. Not again. Yeah, for me it's very hard to actually give a course without ever mentioning the spectral theorem. But it really makes a lot of sense in this case. Let's see why. So here is the spectral theorem, one version of the spectral theorem. You can prove that for every real valued symmetric matrix A, that it can be diagonalized using orthogonal matrices. So this is a very specific form of the spectral theorem. It would work for complex matrices as well, but we don't care about complex matrices. So we have real valued matrices, such as the adjacency matrix. This one is not, it's still symmetric. Is it? No, it's not. Note that if you compute powers of the adjacency matrix, it is not necessarily symmetric. Is it? This one is actually. But if the graph was directed. So for an undirected graph, the adjacency matrix is always symmetric. Right? That is to say that if we were to flip it along the diagonal, this row is exactly the same as this column. And this row is exactly the same as this column. So this is a symmetric matrix. And for matrices like that, we can prove that we can write them in this form. So symmetric matrix. Symmetric matrices have to be square, otherwise they would not be symmetric. Can be written as a matrix U times a matrix lambda times a matrix U transpose, which is the same as the U in front of it, but just transpose. And this is very, very special because this matrix U contains n column vectors. I write them as these vectors U1, U2, up to Un, and they are called the eigenvectors of A. And this matrix lambda is a diagonal matrix where any element of the diagonal is 0, so I'm not actually showing them here. The only elements in lambda that are different from 0 are found along the diagonal. So lambda 1, lambda 2, all the way to lambda n. And these elements are called the eigenvalues of A. Yeah. There's in each and every of my lectures we'll have to, you know that, right? The spectral theory. But now we'll see an application of this you may not have seen so far. This is how you can picture this. So this is your square symmetric matrix A, and it can be written as a matrix U times a diagonal matrix lambda times U transpose. And what is it to say that is diagonalizable by orthogonal matrices? By orthogonal, I mean the two matrices U and U transpose. They are supposed to be orthogonal because lambda is diagonal, so it's diagonalizable using orthogonal matrices. What does it mean for a matrix to be orthogonal? It basically says that if we compute the product between U transpose and U, that is the same as the product of U times U transpose, and that gives the unit matrix. And that is, of course, to say that for orthogonal matrices, the transpose equals the inverse. And you know that because you've been to numerous lectures of mine. So, but if we now want to compute the pth power of A, this is basically to say that we have to compute the pth power of U times lambda times U transpose. Let's write it out. So we have U times lambda times U transpose times U times lambda times U transpose times, and so on and so forth, until we have done that p times. But note that we have inside this lengthy expression here, at some points, products between U transpose and U. But they are 1. So we plug in lots of 1s here. Here's a 1, and then here's a 1, and so on and so forth. So in the end, this power of A raised to the power of P, is basically U times lambda times lambda times lambda times lambda times U transpose. This is because matrix U is orthogonal. But that is to say that the pth power of A is U times lambda raised to the P times U transpose. And interestingly, lambda is an orthogonal matrix, and therefore, if we compute the pth power of lambda, like many of the elements of lambda are 0, nothing will happen. Only the elements along the diagonal are different from 0. And so basically to compute the pth power of this matrix, we just have to compute the pth power of the elements along the diagonal. And that can save a lot of time in practical situations. This is not really important, but now you know about the spectral theorem. That is important because that will come back later. So this was a way for me to sneak in the notion of orthogonal matrices and eigenvectors and eigenvalues, and that will come back later. And there's no excuse for you, now you know what these things are. Okay, quickly, let's talk about Dijkstra's algorithm. What is that? Now we know a lot about graphs, and now we have to think about how to find shortest path in graphs. Dijkstra's algorithm is an informed tree search algorithm that is used to compute path lengths, the length of shortest path, from one node S to any other node in the graph. So it's sort of a 1 to n algorithm. The graph has to be connected, can be directed or undirected, and it must be weighted. And we now know what that means, right? So therefore I had to go through it. In particular, we require that the weights are larger than 0. This is something we need here. So they have to be larger than 0. Who is Dijkstra? You see him, passed away in 2002, is one of the Turing Award winners. Very famous guy. Maybe you have heard of his famous paper, Go-to statement is considered harmful. Very, very influential computer scientist in the early days of computer science. So that is Dijkstra, and he came up with this algorithm here, which is used to compute the length of the shortest path between a node we start from, 3 in our case, to any other node in this graph. And it works like this. We begin by initializing a dictionary. Let's use that terminology we are familiar with from Python. A dictionary of distances. And we initialize it such that it is 0 for the start node. So here, the one colored in red is the node we will be starting from. The dictionary value is 0 for this node. For any other node in the graph, we initialize it to infinity. Okay? And we also, and this is not really necessary if you're just interested in path lengths, but if you're interested in path, it is a good idea. So in the original Dijkstra algorithm is not in there, but we included initialize a dictionary of predecessors. And this one is being initialized to -1 for any node regardless. And then, as I said, it's a tree search algorithm. We have our trusty closed and fringe sets. Here we initialize the closed set to the empty set and the fringe set, interestingly, to all the nodes of the graph. So every node in the graph is in the fringe. And we start with some node. As long as the fringe is not empty, which it is certainly not at this point, right? Because every node of the graph is in the fringe, we select a node out of the fringe for further examination. And the node we select is the one with the lowest distance value. Now, every node has a distance value of infinity so far, except for one node. That is the node S, the one from which we want to start computing shortest path. So at the very first iteration of this while loop, this node U we select from the fringe, the set of all vertices of the graph, will be the node S we are starting with. In our case, node 3. This node we select from the fringe will be added to the closed list and removed from the fringe. And then we will consider every neighbor of this node, unless it is in the closed set. So all the neighbors of this node that are not yet closed will be examined. In particular, we'll check if the current distance value of this node, say infinity, is larger than the distance value of the node from which we have expanded this one, 0, right? So this one has a distance of 0, this one has a distance of infinity, is larger than, in this very first case, 0 plus the edge weight, which is some number hopefully less than infinity. Say it's the distance between two spatial locations attached to these nodes. If the current distance value is larger than the distance value of this node plus the length of the path from here to there, it's a weighted graph, then we update the distance of this node to this value here. And we say that the node U we expanded is a predecessor of V. Right? What happens if we run this algorithm on this graph? Let's see. We start in this node. All nodes have a distance of 0 except for this node has a distance of 2. Every node has a predecessor value of -1. We do this, so we have entered this while loop, we have selected the red node, and you have seen that these numbers have switched. Right? The numbers of the neighbors of node 3 have switched. Let me switch them back and forth, back and forth, back and forth. You see, switching. Okay, so these numbers have switched because we are in this for loop right now. We have found that this node is a distance of 0.8 by, it was infinity, but now we have set it to 0.8. That is the 0 of the node we are coming from plus the distance, which was obviously 0.8. And accordingly, we have also updated its predecessor. We have done this for the other two neighbors of that initial node as well. Now, actually what I am missing here is the extension of the fringe. No, it's okay. We're not talking about A star here. The fringe contains all nodes, so I was ahead of myself. In the next iteration, so we are done with the first iteration. In the next iteration, we select the node of the fringe that has the lowest distance value. It happens to be node 7. Now every node 7 has 3 neighbors. This one has been explored already. This one is a closed list, is a red node. And these two nodes already carry distance values and predecessors. And let's see if something changes. No, it does not. Because apparently, they are not, there's nothing to do for us here. They are not closer to 7 than they are to 3. So we continue the while loop. And are going to explore node 6. There's nothing to do at all because none of the neighbors of 6 is not in the closed list already, so nothing happens. We continue with the while loop. We find node 1, which is now in the fringe, the node of closest distance to the node we started from. We have to enter this for loop, so every neighbor of node 1 that is not yet in the closed list will have to be updated with respect to their distance and their predecessors. Let's see. There's the update. And now we continue the while loop. This one is the one with the closest distance to node 3 so far in the fringe. Let's see if something happens. No, nothing happens. This is the next iteration of the while loop. This is, oh, no, something happens because this node has a neighbor that has not been considered by any such for loop. So now from node 2 we have to update the values for node 5. Then we continue with the while loop. It is node 1. Then we have to update node 8. Yes, that happens. We continue with node 8, which is the closest node in the fringe to node 3 according to the distance values, because 3.0 is less than 3.2. And from there we can update node 10, which now is at a distance of 4.8 from the start node. And now something interesting happens, because the next, and this is why I have to run this example so many times, next interesting thing that happens is now we will explore node 5, because this one is carrying a distance value of 3.2, which is less than infinity or 4.8. So this will be the next node to be considered, yes. And now we are going to consider the neighbors of node 5. And note that if we do that, the distance currently assigned to 10 will be updated. It's 4.4. Right? 9 and 10 are not in the closed list yet. And we have examined node 10 already when we looked at node 8, and there was a new distance value assigned to node 10. It was reduced from infinity to 4.8 because that is the length of the path to 10 from 3 over 8. Now we are considering node 5, and it turns out that the current distance of node 10 is actually larger than the distance currently assigned to node 5 plus the distance from 5 to 10. So it will have to be updated. Yeah, it's 4.4 now instead of 4.8. So this is the ingenuity of Dijkstra. He came up with his algorithm. Now we have to expand 2 more nodes and then we're done. That is, once this thing is done, we know the distance between every node in the graph and the node S, in our case 3, we started with. And not only do we know the distances, but for every node we also know the predecessors. We introduced this additional dictionary P here. We can use that to compute a shortest path. Basically have this function shortest path, which we call with what is this P? It's the dictionary of predecessors. The starting node, 3, and the terminal node, in our case, say 10. And we, once entering this function shortest path, initialize a stack data structure to the empty stack. And then we look at the p-value of node t, which is 10, and the node is node 10, and the p-value of 10 is 5, so apparently the predecessor of 10 is 5, the predecessor of 5 is 4, the predecessor of 4 is 1, and the predecessor of 4 is 3, so we have found a path. Yeah, there you go. Ever so quickly, because we have to sort of speed up a bit, this is a bit of a costly algorithm, can be tremendously improved using very fancy data structures, Fibonacci heaps, very fast on directed graphs, but can be even accelerated further if we just want to compute shortest path and not the distances between a certain node and any other node. What we basically have to do is, like, you know, terminate that while loop earlier and try to examine nodes that lie in the wrong direction. Right? When we started this, say we want to find a path from 3 to 10, why should we look at 6 and 7 in this example? So let's look at a solution which is called the A-star algorithm. Was introduced by Hart, Nielsen, and Raphael. A very, very famous algorithm. I'll come back to that later. Here it is. This is an algorithm that is being used to compute shortest path. It's not to compute distances, shortest distances between any node and any other node. It is tailored towards the problem of computing the shortest path from a start node to a target node. This time, again, we initialize the closed set to the empty set, but the fringe is now the set just containing the start node. Right? And then there is something special. What was called D in the Dijkstra algorithm is now called G. But this is just for historical reasons. I should call it D because that is what it contains, distances, but in that paper it was called G, so everybody calls it G. The G here is nothing but the D previously. So this is G contains the distances. And we have another dictionary. This one is funny. It's called F, and it is the sum of G plus some H. This H is what makes this A star special, and we will look into this later on. Again, we iterate a while loop while this fringe is not empty. This time we start with a fringe of just one element. From this element, we have a look at all the successors. So basically we, again, use the element of the fringe with the smallest, this time f value, not the distance, but this f heuristic. But we look for the smallest, just as in Dijkstra. Remove, if you know, that node we consider for further expansion that we just selected from the fringe coincides with our target node, then we stop. We're done. We have found the solution. If that is not the case, we remove the node we just selected from the fringe and add it to the closed list, as always. And then we look at all its neighbors, if they are not in the closed list already. And well, then we check if, okay, so we first compute a new distance, just as we did with Dijkstra for each of the neighbors. We compute, it's called G, but it's the distance. So we compute a new distance for the node we are currently considering, V, as the distance assigned to the node we started with, plus the edge weight between the node we just came from and the one we are considering now. So this is just as in Dijkstra. If this neighbor is not an element of the fringe, or its current distance is larger than the new distance, in this case we update the distance of this node, just as we did. And then we also have to update this f function. Right? This is basically, we take the distance value we just computed and add something to it. Some function h that depends on the node we are currently exploring and the target. And we also update the predecessors, and if it so happens that that node was not in the fringe yet, we add it to the fringe. In the next iteration of this algorithm, we this time blissfully ignore these two nodes, because if you look at it, this additional h here caused the function f for these two nodes to be larger than for this node. And it's not about just the distance, but it's the distance between this node and this node plus some h of this node and the target node, say 10 in our example. And because this additional term here causes the f values of these two nodes to be larger than the f value of this node, and as we are looking for the node with the smallest f value for further expansion, they will not be expanded at this point in time. But instead the A star algorithm expands this node. Okay, now we consider this node and all its neighbors. We compute the g, h, and f value, of course, for these neighbors. And then we, yeah.
I may be mistaken, but your algorithm break at that point.
Hmm?
Because like we are taking u as an arc mean of fn where nr is in fringe, right?
Yeah, yeah.
So in our case, in the second step we have 3 and 1 in the fringe, and fn is described as g plus h, right? So g for the 3 is f for the node 3 is 4.2,
yeah,
and for the node 1 it's 4.3, right? Yeah,
no.
sorry.
Yeah, 4.3, yeah.
And so we are taking arc mean,
Yeah.
and it means we'll take 3 again, and we'll have u.
Oh, but it's in the closed list. 3 is in the closed list, and if it's not in the closed list, then we don't care. We have put, removed 3 out of the fringe and put it into the closed list.
Okay.
This is what we always do. If we consider one thing for expansion, we remove it from the fringe and put it in the closed list. So therefore, it will not be considered anymore. Here we just consider nodes that are in the fringe. Right? And look at it. So, for instance, like why would we expand 1? Because if we add 0.5 and 4.2, that this is 4.7, which is larger than 1.1 and 3.2.
I missed the step of removing.
No. Once we have selected a node for expansion, we remove it from the fringe. Right? So we continue again. So say we had this node. It had 3 successors. They are all in the fringe now, and out of the fringe we select node 1 for further exploration. It has 3 neighbors we have not yet considered. They will be added to the fringe because they are not in the fringe yet, so they will be added to the fringe. And there, again, we have to look at their f values, which is the sum of the distance plus something else. And then, in this case, node 2 will be selected, and from there, node 5 will be expanded. Is the only neighbor of node 2 that has not been expanded yet, or considered, put to the fringe. And then something interesting happens now indeed, like even though if we visually would say 5 is closer to our destination of 10, the algorithm first goes for 4. From there, considers node 8, and then finds that of the 2 fringe nodes that are sort of the ones with the smallest f value, now 5 is actually the one with the smallest f value. From there it considers 10 and 9, and then it has found node 10. So this is what the A star algorithm does, and the really crucial thing is that we are not just looking at distances between a node and the source node we are coming from, but we are looking at distances between a node and the node we are coming from plus something else. And this is called H for sort of heuristic. We see this is a best first search algorithm. It selects an arc min out of the fringe, so there's some optimization going on. And these nodes for expansion are selected according to this f function, which consists of a measure g of the path coast from where we started to where we're at right now. So this is the actual cost of the path from node S to node N. And then there is H, an estimate of the future path cost. Now we are at some node n, what might it cost to get from here to the target? So this is the future path cost from n to t, and we don't know that because we have not explored the graph, but we can estimate it. Right? And the estimate that is typically used in path planning is the Euclidean distance. So if all the nodes were labeled with their spatial location, and we know we want to reach T, say Bremen, we can compute the line distance, the Euclidean distance between, say, Münster and Bremen. There is a distance. We don't know if we have to go via Osnabrück or Hannover yet, but there is a distance between Münster and Bremen.
So its direct distance doesn't matter whether it makes sense or not?
It's a very important question he asked. Does it matter what we choose for this H? Yes, it does. But as long as this H is admissible, and this is another definition, if it is admissible, it does not really matter. It doesn't matter from a practical point of view, but not from a general point of view. Such a heuristic function, H, is called admissible if it does not overestimate the cost of the future path. If it underestimates the cost of the future path, then it's admissible. And now remember what we learned about distance functions last time. They have to, fulfill the triangle inequality. So we are in, say, Münster, want to go to Bremen. We could go either straight or via some other node. And of course, there might be no direct connection between Münster and Bremen, so the straight line is not available to us, but there might be a path going over another node. But this direct, if it was there, even if it's not, it's shorter than the actual distance we have to travel. So the Euclidean distance is indeed admissible. It never overestimates the actual distance between two nodes if we cannot reach them directly, but underestimates them because of the triangle inequality. And so yeah, this C denotes the path. So H is called admissible if it underestimates the true costs, which we do not know right now. But because of this property of the triangle inequality, we can say H must be admissible. Right? This is a basic property of distances like that. So in the context of path planning, H is typically chosen to be the Euclidean distance, because we know it will not overestimate the true distance. One can show, and this time I'm not putting it in quotation marks because actually we'll do it, that this algorithm is optimal and complete. In path planning, Euclidean distance is an admissible heuristic, and A star is the de facto algorithm for path planning. There's like hands down, path planning is done with A star. There are clever extensions of it and variations, so you can use A star in bidirectional searches and so on and so forth. But path planning at its heart is done using this algorithm. Well, I said I'm going to prove this to you in the interest of time. I will not. But this is trivial. This is so trivial. It's embarrassing. This is really trivial. This is the lemma A star is optimal, and this is the proof. Look at it at home. I'll skip it because of time. So this is the first part of what you can prove that A star indeed is optimal. It will find the optimal solution. It will never find a suboptimal solution. It will always find the optimal path. Very simple proof. Here is the other one. If basically the graph is finite, that is, if the branching factor is not infinite, and if the path weights are larger than 0, in this case it's also complete. Right? But these are very reasonable assumptions for practical purposes. Like in the real world, there's hardly anything that is really infinite, and distances between, say, cities are larger than 0. So these things are given. If they are given, it is also like it's even self-explanatory that this is indeed complete. So to wrap it all up, today we have looked in detail in many more terms and definitions from the area of graph theory, and this is because we are currently studying problems of pathfinding. Pathfinding problems can be easily cast in terms of graph search problems. So when talking about pathfinding, we have to talk a lot about graphs, we have to talk about labeled graphs and connected graphs and stuff like that. And now you know what all these things mean, or at least how they are defined. You know what a connected graph is, you know what a labeled graph is, and so on and so forth. We have seen for the first time in this lecture the spectral theorem, but it will come back, obviously, you know me. And one of its many, many applications. So we have seen that we can use the spectral theorem and apply it to the adjacency matrix of a graph, so to factor it into two orthogonal matrices and a diagonal matrix, which gives us a very convenient way of computing arbitrary powers of the adjacency matrix. We looked into Dijkstra's algorithm for computing path length in a graph. We sort of abused it a bit and introduced this predecessor dictionary so that we can also actually compute path. But this is basically an algorithm for computing the length of path between one node and any other node in the graph. Beautiful algorithm, like the underlying concept is really great and very elegant. But of course, if we are just interested in the shortest path, this is a bit of an overhead. And so therefore we looked into the famous A-star algorithm. Really, this is a staple of artificial intelligence. If somebody would have to come up with a list of the 5 most important accomplishments of artificial intelligence, this would rank among the top 3. This is how the A-star. Yeah. This is definitely one of the 10 most beautiful algorithms in all of computer science, the Dijkstra algorithm. But the A-star is probably one of the biggest accomplishments in artificial intelligence. And like seriously, you cannot even read a paper or book or website or blog entry on game AI that does not at least mention A-star. Because to them, it's sort of the pinnacle of AI. Right? No, this is the method of choice for path planning these days. And all the route planning devices and software you're using on your phones or in your car or whatever, they basically rely on A-star and variants that, of course, there's always room for improvement, right? But at the heart is the A-star algorithm. And this is an algorithm that indeed computes shortest path. You are given a graph that is labeled or weighted. You have a source node and a target node, and this algorithm will find the optimal path between the source and the target in finite time, if the graph is finite. And yeah, it will definitely find the optimal path. So these are guarantees, which you can look at the proofs, they are trivial. That is all for today. Was a bit rushed at the end, but we'll come back to that next time. Are there any questions? Okay, if not, then I guess it's Monday.